Hi, my name is Philipp Sudek and I am a third-year PhD student at the University of Portsmouth, supervised by Adam Amara. Today I am very happy to share with you the results from the recent paper that me and my colleagues have been working on. In this paper, we investigated the sensitivity of the redshift distribution to galaxy demographics. To start, let's begin with a short introduction and motivation of this topic. Many cosmological probes, such as weak gravitational lensing, depend on accurate redshift distributions of galaxies. The most precise way to determine the redshifts of galaxies is using spectroscopy. Using absorption and emission lines, one can calculate the redshifts of the corresponding objects very precisely. However, the spectroscopic redshifts are not a suitable choice for current and upcoming experiments like the Dark Energy Survey, the Hypersuprime Cam of the Subaru telescope, or the Sloan Digital Sky Survey. The big areas and depths covered by these surveys make spectroscopical redshift measurements extremely time-consuming and cost-intensive. Photometric redshift measurements are an alternative for such big surveys. Photometric redshifts are commonly determined in two ways. First, we can fit spectral energy distributions in different broadband filters. Second, we can use machine learning methods that are based on samples of known redshifts. However, the precision of photometric redshifts is quite low compared to spectroscopic redshifts, and this decreases the constraining power of cosmological probes that rely on photometric redshift measurements. Now, often one just needs the redshift distribution and not each individual redshift for cosmological probes like weak gravitational lensing. Herbal et al. Developed a method in 2017 to simulate the redshift distribution with a forward modeling approach based on Schechter luminosity functions. Using approximate Bayesian computation and based on a forward modeling approach, Herbal et al. Inferred a posterior distribution of the redshift distribution from image simulations of Subaru data. Then, they compared the posterior to an estimate of the redshift distribution from the Cosmos 2015 catalog, which we see in the image on the left side. It confirms that the method provides a good measure of the redshift distribution of cosmic shear-like galaxy samples. In the plot, the black line shows the redshift distribution estimate n of z from the Cosmos 2015 catalog. The color-coded lines correspond to the posterior distribution obtained with ABC, and the prior distribution is shown in the gray lines. The colored vertical lines represent the mean redshift of the corresponding redshift distributions. We can see that the Cosmos redshift distribution is very well contained within the posterior distribution. Important is that in this method, gaining n of z is solely sampled from redshift-dependent Schechter luminosity functions. So let us take a look at the Schechter luminosity function itself. The Schechter function describes the number of galaxies per co-moving volume and absolute magnitude m. The function is redshift-dependent and is mainly characterized by the amplitude phi star, the characteristic magnitude m star, and the faint end slope alpha. If we take a look on the example plot, alpha defines the faint end. Phi star is the normalization, and m star defines the point of exponential drop-off at the bright end. This corresponds to the magnitude at the normalization point. The model described by Herbal et al. In 2017 uses a linear functional form for the characteristic magnitude depending on the redshift. Further, they take the amplitude phi star as an exponential function of redshift. While keeping alpha constant, that makes four free parameters: am, bm, a phi, and b phi. The model also considers two galaxy types, star-forming and crescent. The different populations are described by different Schechter functions, and therefore we have 8 free parameters. Previous studies like Tortorelli et al. From 2020 and 2021 included constrain for these parameters. However, some of the parameters have very large uncertainties, which translate into the simulations of the redshift distribution. In our recent paper, we analyzed how these uncertainties are affecting the simulations of the redshift distribution. The main goal was to study the sensitivity of the redshift distribution of sets of galaxies to the model parameters. The motivation was to better understand which model parameters need to be well understood to make the next generation of precision cosmological measurements. But before we come to our analysis, let me briefly talk about how we use the forward modeling approach in our work. To run our simulations, we use the open source Python package SkyPy. SkyPy comprises a library of physical and empirical models to run end-to-end simulations of the astrophysical sky. It provides a framework for simulations of a range of cosmological probes like galaxy populations, large-scale structure, and gravitational waves. SkyPy is already able to run galaxy simulations and produce synthetic data with different galaxy properties. The development of SkyPy is driven by R&D projects like ours, which develop new functionality of the package. In addition to this, we are always open to external contributions. In our work, we extended the package and used it to run simulations of galaxy catalogs including redshift, absolute magnitudes, and the parent magnitudes that match observational data. Currently, our team is also developing other sources like halos, supernovae, and gravitational waves. In addition to all of this, any user could run the SkyPy pipeline runner to produce their own simulations with their own implementations. To perform our analysis, we run a set of simulations of the redshift distribution with a fiducial set of parameters. Then we change the value of one parameter by increasing its value by its given error sigma. Afterwards, we compared the new redshift distribution to the fiducial redshift distribution and then repeated the process by also subtracting the error from the fiducial parameter value. This resulted again in a different redshift distribution, which we compared to the fiducial redshift distribution. We then repeated this process for all parameters individually because this enabled us to investigate the sensitivity of the simulated redshift distribution to each parameter. We did this analysis for 3 different survey types: SDSS-like surveys, DES-like surveys, and HSC-like surveys. In this way, we studied the differences of the sensitivity to the parameters for surveys of different depths and field of views. Note that the sensitivity is meant to be relative to the ability of modern datasets to constrain the parameters. After analyzing each parameter for each survey, we could identify the parameters that have the strongest impact on the simulated redshift distribution. On the right side, we see a plot comparing the fiducial and test catalog after modifying 3 different parameters. The individual columns show the result for the different surveys, and the rows correspond to the parameters that were modified. The black lines correspond to the fiducial redshift distributions that were simulated with the default set of parameters. The red curves show the simulated redshift distribution after adding the parameter error to its value. Accordingly, the blue curve resulted after subtracting the error from the parameter value. Comparing the impact of the parameter modifications on the different survey types, we see that there are different sensitivities depending on the experiment. Changing one parameter can have a big impact on the redshift distribution of one survey type, but not on a different one. Let us focus on the first row, which shows the results after investigating the impact of AM for star-forming galaxies. We can see that generally a modification of AMSF affects the redshift distribution of each survey, but the amplitude of this change is very different. Whereas the differences of the test and fiducial redshift distributions are very minor in case of SDSS-like surveys, the impact of AMSF on DES and HSC-like surveys is very strong. This observation follows from the variety and the depth of the survey. SDSS-like surveys have lower magnitude limits than DES and HSC-like surveys and measure mostly closer galaxies which have lower redshift values. However, AM is describing the redshift evolution of the characteristic magnitude. Therefore, variations of AM directly affect the bright end of the luminosity function and changes the abundance of high redshift objects. Following from this, the effects of AM are more evident in DES and HSC-like surveys as they have fainter flux limits and measure more high redshift galaxies. Generally spoken, we observe that SDSS-like surveys are more sensitive to parameters of the quiescent population, and DES and HSC-like surveys are more sensitive to the star-forming parameters, which matches our expectations. Let us now take a deeper look on how strong the effects of the parameters are. Since upcoming surveys are quite similar to DES, we focused on the three parameters that a DES-like redshift distribution is most sensitive to: AMSF, AFIQ, and BMSF. The parameter that has the biggest impact on the redshift distribution is AM for star-forming galaxies. Looking at the upper panel in the middle column, we see that decreasing AMSF by its error, the blue curve, results in a very distinct redshift distribution compared to the fiducial one, the black line. Also, the red curve, which corresponds to an increase of the parameter value, deviates from the fiducial curve. This indicates that for the application of simulated redshift distributions in future high-precision experiments, AMSF needs to be better constrained. But how do these changes of the redshift distribution look like quantitatively? To compare the test and fiducial redshift distribution quantitatively, we looked at the changes of the mean redshift. Generally, the numbers agree with the differences that we saw in the previous plot. As discussed earlier, AM has the biggest impact on all surveys. The redshift distribution of the DES-like survey showed the biggest sensitivity to a decrease in AMSF. The mean redshift changed by about 45%, which corresponds to a shift of 0.3 units. This value was by far the largest in our whole investigation. Such a high value can cause strong bias in cosmological constraints when using weak lensing observations and the forward modeled redshift distribution. Because of this, and since upcoming surveys like Euclid and LSST have similar properties as DES, our investigation shows that AMSF is the most important parameter that needs better constraints in the future to use this approach in next generation experiments. The other parameters have less effects, but our results suggest that most of the other parameters need better constraints as well. So far, we learned which parameter has the strongest impact on the redshift distribution of DES-like surveys. But how does this affect actual measurements? Using the same set of simulations, we also investigated the sensitivity of the magnitude and color distributions to modifications in AMSF. In this way, we saw how the parameter impacts observations, and we can get information which observables could be useful in constraining the parameter. This plot shows our simulated 2D color and magnitude distributions in the DES filter bands G, R, I, and Z. The black contours and lines correspond again to our simulations with the fiducial parameter set. Blue and red represent the galaxy catalog after subtracting and adding 3 times the error to the value of AMSF respectively. We see that the effect that we saw in the redshift distributions is generally translated into the observables. However, we needed to make the parameter modification larger because the effects are smaller here. The different observables also show different sensitivities to the parameter change. Focusing on the magnitude distributions in the bottom right corner and the color distributions in the upper left corner, we observe very small sensitivity. On the other hand, we see larger deviations of fiducial and test catalog in color magnitude space. Especially, decreasing the parameter results in a very strong change in the distributions. Quantitatively, we compared the distribution using the Anderson-Darling test. The results support the observations in the plot, and they showed that the color magnitude combinations have the highest sensitivity. The choice of color magnitude pair has a minor role because the sensitivities are very similar. Now we are reaching the end of my talk, so let me give a small summary. I started showing the problems of current galaxy redshift measurements and demonstrated that for some cosmological probes, like weak lensing, where you only need the redshift distribution, the measurements can be replaced by forward simulations of the redshift distributions. I showed that the method developed by Herbel et al. In 2017, which is based on redshift-dependent Schechter luminosity functions, is very suitable for this purpose, and that simulations based on this model can be run using the Python package SkyPy. However, the luminosity functions in this model are not very well constrained yet. In our recent work, we studied the impact of these uncertainties on the simulated redshift distribution of different survey types. We showed that for upcoming high-precision experiments, it is most important to constrain the slope of the characteristic magnitude AMSF. At the end, we further explained that the uncertainties are mostly translated into the 2D color magnitude distributions. This means that observations of these quantities could be helpful in constraining the parameter in the future. Thank you very much for listening.